computer science from the University of Illinois at Urbana-Champaign. His main areas of research are distributed systems, multimedia communication, network support for systems management, network monitoring, system diagnosis, and software-defined networking. He completed his undergraduate from Bangladesh University of Engineering and Technology. During summers of 2010 and 2011, he worked as a research intern with the Autonomic Management Group at NEC Labs. And he's also spent the summer in 2012 as a research intern at Microsoft Research. He's published his research in top distributed systems, networking, and multimedia systems conferences. He's a recipient of the Best Student Paper Award in ACM Multimedia in 2011, and his work on 3D video optimization has been selected as a notable paper in computing in 2012 by ACM Computing Review. So I guess with that, I'm going to go ahead and turn it over to Dr. Arefin. So Ahsan, please take it away.
Thank you, Sridhar, for the introduction. So today I'm going to present our work I have done in the area of session management in 3D tele-immersion. So since we have a very cozy group, please interrupt me at any time if you have any question. Now, before going in detail about our work, I will first start by defining what is 3D tele-immersion and what are the specific challenges we try to address in this talk. And then we'll go some of the work that we have done to address these challenges. So 3D tele-immersion is a distributed platform that brings geographically distant users to interact with each other in a single room-like environment. Both industry and academia have developed their own 3D tele-immersive setup for commercial purpose as well as for research usage. For example, in EYUC, our lab, we developed TV, which is an abbreviation of tele-immersive environment for everybody. And in 3D tele-immersions, users' 3D images are captured in real time and merged in a virtual shared environment for remote interaction and collaboration. Now, due to this rich audiovisual interactive context, the application of 3D tele-immersion is not only bounded for video conferencing. We have seen application in other domains as well. For example, we have used the system in multiplayer gaming where distance people can play with each other in the virtual environment in real time. We also have used the system in case of collaborative dancing, where geographically distant dancers can dance with each other in a virtual environment to build a synchronous collaborative art. We also seen application in 3D live meeting as well as in remote learning. Now, in remote learning applications, a user can get merged into a virtual environment and to show other remote peoples how to use how to mount and dismount a complex object in the virtual environment. In 2013, NSF has focused or contributed a big amount of research funds to use 3D tele-immersion in the medical domain to provide support to the patients immediately or emergency situations where doctors are not immediately available. Now, to understand the complexity in session management of 3D tele-immersive applications, we first need to understand what are the unique characteristics that are not addressed by current solutions. So the characteristics we look into, the first characteristic is heterogeneous users. In 3D tele-immersion, we have two types of users. The first type is immersive users, and immersive users are the users who interact with each other in real time to form or to perform a collaborative task. And each immersive user is surrounded by a number of devices that includes camera which generates 3D images, audio devices, and renderers. Now, this stream generated from each immersive users need to be disseminated in real time to allow real-time interaction and collaboration. Now, in addition to those immersive users, we have a set of non-immersive users, and the number of these non-immersive users can be very large. The non-immersive users are the users who only watch the activities performed by the immersive users on their screen. However, they do not contribute any stream into the virtual environment. Due to this non-immersive nature, the end-to-end delay can be flexible. However, we want to ensure that the quality of the video or the immersive experience that the non-immersive users receive is much better so that the user satisfaction is confirmed. Now, if we look into the immersive users and non-immersive users, both uses a special node which is marked as G. We call it a gateway, and the gateway is responsible for disseminating the local streams as well as for receiving the remote stream for rendering purpose and for collaboration purposes. Now, the second characteristic is 3D tele-immersion support a multi-stream and multi-view environment. Here we give an example of how multi-view looks like when you take stream from different 3D cameras. Now, depending on the remote user views and the spatial physical placement of the cameras, there is a spatial dependency among the 3D streams. Here in this example, when a user is looking with a specific views or a specific view orientations, you see that the cameras, the stream generated from camera C3 and C4 are more important than the stream generated from C6 and C7. Now, if the remote user change his or her views, this spatial relationship changes, and the relative priority of the streams will also change. And this information is important when you want to use 3D tele-immersion in a domain when the requirement on the availability of resources are limited. Now, the third properties we look into is correlated multi-stream dependencies. Now, this dependency exists within a single site as well as across the sites or participants we use in 3D tele-immersion. For example, if we have a camera to capture the upper body of the image and a camera to capture the lower body of the image, we must need to synchronize these two images so that we can create a consistent view of the person's 3D model. Similarly, the dependency exists across the sites. Here I give an example of an immersive session where two persons are performing a lightsaber dual activities. And we see the frame numbers generated across different times. Now, if a non-immersive user wants to watch these activities on their screen, and if he fails to maintain the dependency on his screen, he will get a view which actually never happened into this 3D TI domain. So we also need to maintain this across the site dependency of the streams. The fourth property, which is very obvious, is the high demand of network resource, since we are using 3D images to disseminate from users to other users. For example, in our TV systems, if we use frame resolution about 320 and 240, and for each users or participants, we use 4 3D streams, and with the increasing number of users, the requirement of bandwidth becomes very high, where with 6 users, the requirement of total bandwidth to participate in a 3D tele-immersive session is about 76 Mbps. Where if you use a single stream-based Polycom HD video conferencing solutions, the requirement of bandwidth for 6 participants is about 13.8 Mbps. So we need to properly allocate resources so that we can ensure the usage of the resources we want to use during the session runtime, as well as we can improve the experience of the users when they are participating in the session. The fifth unique property that the 3D tele-immersion poses is the activity-dependent user expectations. As we mentioned before, we can use 3D tele-immersion for different activities. We saw that when people are performing different activities, their expectation of quality of service becomes different. For example, if they use the system for video conferencing applications, users are more concerned about the audio-visual skew. They want to get at least the good quality of the image for the upper portion of the body, which represents their visual face. However, if they want to use the same system for virtual lightsaber activities, they're not much concerned about the audio-visual skew, rather that they want the full body of the image with a reasonable quality of the 3D model. Similarly, if we change the activities, the requirement of quality of service will also change, as well as we'll see there's certain priority we need to guarantee depending on the resources we have. Now, based on these characteristics, 3D tele-immersion poses some unique session properties, which includes multi-stream spatial dependencies we need to maintain. We also need to maintain multi-stream temporal dependency across the site as well as inside a site. We also need to allow frequent multi-party view change, since during the session runtime you can interact with a remote person from different view orientations. We need to maintain a proper algorithm to accommodate resource usage in the session runtime. And as well as we need to ensure that we can maintain quality of service differentiations, which maximizes the experience of the users. And based on these session properties, we define the session functionalities that we need to maintain in 3D tele-immersions. We need to identify the data plane behavior of the session, which concludes session monitoring. We need to identify multi-stream routing configurations. We need to solve dynamic view change provisioning and adaptive QoS and resource allocation. Now, session management is a very old domain where people are trying to develop different session management protocol. For example, we have session initiation protocol or SIP, session description protocol or SDP, and RTSP or real-time streaming protocol. Now, those protocols were originally designed for a single streaming solutions, but in our case, we have a multi-streaming case where the requirement or the challenges are different. Now, later on, the solution has been proposed to improve the single stream-based session management protocol towards multiple stream, including the recent IETF effort to build a session management architecture. However, still the spatial dependency, the quality of service differentiations are not properly addressed in any of the current work. So in our research, what our goal is, we want to consider or build a user experience-aware programmable cross-layer session control framework to support user heterogeneity, that means the immersive user and non-immersive user requirement, quality of service dynamisms, frequent view changes, real-time interactivity, multi-stream dependency, and high resource utilization. So we'll show, we have three objectives that define the session management framework or control framework. One is user expectation aware, so that we need to identify different level of experience or quality of service allocations depending on what kind of user we are using, what kind of user are using the systems. The session management should be programmable in the sense that you should be able to allow change of the session configurations when user changes views or activity gets changed. And at the end, we'll show the cross-layer configurations by taking the support of the network layer and building a synergy from session and network. We can further improve the real-time interactivity and resource utilization. So my research is focused on given a data plane which includes immersive users and a set of non-immersive users. How can we collect this session and performance monitoring data? And during the session runtime, when you have the session request, which we call programmable session parameters, and using this information, how can we configure the session that meets user expectations? Now, session configurations we divide into three parts. The first is we want to identify how we want to perform non-immersive session configurations. And also we want to identify how we want to perform immersive session configuration as well as network layer configuration. So my research is divided into 4 different groups. I
have a question.
Sure, go ahead, please.
Hello?
Yes.
I had a quick question. The user expectations, is
Yes.
that like a quantitative metric somebody is giving, or how does the user express their expectations?
Right. We'll discuss about more detail about it. It's a quantitative metric or subjective evaluations we perform to build the quality of experience.
Okay.
Ahsan, before you jump in, folks, there is quite a bit of ambient noise that is coming, so if you guys can keep your telephone or your microphones muted and only unmute yourself when you ask questions, that will be awesome. Thanks.
Okay, thank you, Sridhar. So at this presentation, I will only focus on the immersive session configuration using OSM and the immersive network configuration using OpenSession. So before going into detail of our solutions, I'll first give an overview of how our session management architecture looks like so that we can follow when we discuss about specific solutions. So our session management architecture contains a hierarchy of controllers, and at the top of the hierarchy is the global session controller or GSC, and each user, whether it's the immersive user and non-immersive user, uses a local session controller or LSC. Now, LSC is responsible for monitoring or configuring the local session at each users or participants, and GSC is responsible for maintaining the global resource and allocating or optimizing this global resource. For non-immersive users, we due to the scalability reasons, we classify them based on a metric and group them, and for each group we assign a group session controller which works as a GSC for that group, and this GRSC coordinate with each other via GSC. Now if we look into the immersive user configurations, each LSC also has another part besides LSC, which is called NC or network controller, which is responsible for allocating the network layer components during the session runtime. So in this presentation, I will focus on the left side of the architectures, which is including only the immersive users. Now, what is the immersive session configuration really means? Now, if we look deeply into the distributed architecture of 3D tele-immersions, the goal is that you have a number of users, and each user has a number of input devices and output devices. So the goal truly is how can we relate the input device to the output device using some kind of distributed manner. So relating means, for example, we want to send the camera stream from site X and send it to a renderer of site Y. and other camera streams, we want to send it to site Z and site Y. So truly our goal is to build a dissemination or multi-stream dissemination architecture that reflects this requirement. And we propose a OSM or optimized session management architecture. It includes a global session controller, as we mentioned, which is a global coordination plane that monitors the data plane and then configures the data plane based on the input and output relationship requirement during the session runtime. And to build this architecture, we use a session routing table, or SRT, where the SRT includes three fields: match field, forwarding actions, and forwarding rates. And using these three fields, we can define any multi-stream dissemination graph, where the match field defines what is the streams we want to forward. Forwarding action defines what are the gateways address we need to forward it to, and the forwarding rate defines what is the rate we need to use on these forwarding purposes. And using this SRT, we can build a multi-stream dissemination graph where the SRT is computed by the global session controller. Now, to understand how this whole process works, we'll go into the details of the global session controller architectures, which includes three functional components. One is stream metadata and participant manager, which is responsible to identify the spatial relationship of the streams as well as the participants currently in the immersive sessions, and what are the devices they have and what are their capabilities. Next, the QoS policy and constraint manager identifies what is the quality of service we need to maintain during the session runtime. And finally, QoS allocator and topology constructor builds the topology and configure the data plane to reflect a specific multi-stream dissemination graph to maximize the quality of experience. So the whole process works is you get the resource monitored from the data plane, you have the views and activity session demands from the user during the runtime, and when you have these all informations and the topology is constructed, the GSC sends the session routing table to the LSC, which conveyed to the gateway in the data plane, and then the streaming is performed. Now we'll see how different components work. So the first is stream metadata and participant manager. So as I mentioned, the responsibility of this component, yes.
A quick question. I'm assuming this SRT needs to keep getting updated. This is not a static one-time thing, right? I mean, it's something that has to keep getting computed as the topology, as people leave and people join, etc.
Right.
As the immersive users change configurations. Is that correct?
Right. Okay. So, so the next point, another component we focus in here is that how we can maintain or build the spatial relationship among streams. And we can go into the example we described before, that you want to capture the 3D stream of the participant and disseminate it to a remote participant for the rendering. Now, when you have the resource bounds or limitations, you should consider the user views to optimize your contents. Now, here in this example, given the user view, you can identify which streams are contributed more to the view and which streams are contributed less. And when you have a scarce resource, you can drop the less important streams in the dissemination purpose. Now, how do we find this relationship during the session runtime? We consider two vectors. One is the field of view vector, and one is the camera, the view orientation vector of the remote users. In using these two vectors, we can compute the angle between these two vectors, and we can define a matrix called local priority, which is a dot product of these two vectors. And as you can see, the smaller the angle is, higher the priority. So using this value, we can define what is the priority of the different streams we're using from a specific site. So if we want to only send 4 streams for a given view, we can define a set of streams according to their priority that we want to disseminate them. And in case of resource limitations, we can drop the lower priority stream. Now the question is, since we are using or dealing with multi-party immersive applications, how can we define a global priority? That is, how can we define the priority of a stream from site A and how priority of a stream from site B, and what is the internal what is the relationship between these two streams in terms of priority?
Ahsan, a quick question again.
Yes.
I guess conceptually, why is it that the smaller the angle, the lower the priority?
Because as you can see from the view orientations, when you want to watch from a specific view, the camera which has the lower angle with you will cover the most spatial domain that represents to your view. If you look into the figure, right?
Okay.
For a given view, when you have this triangle and the C8 that contains this triangle, it covers most of the view, most of the portion of the persons that the view should include.
Okay, thanks.
So now using the, if we have two different sites, site A and site B, and you have them all in the local priorities. What you want to do, you want to build a global set where the first two streams from the local priority should come first, and the next two streams from the local priority should come next in the global priority. And to maintain these relationships, you don't want any kind of arbitrary ordering where you want only maintain the local priority. Because in the stream that I just cross out, here the stream's ordering maintains the local priority but not any global. So we also include a priority index concept where each stream in the local domain is marked as the value of depending on the number of total stream into the site. So the stream that has high priority will take the value of the value equals to the total number of streams, and then as we lower the priority, the value will decrease monotonically. And this lower priority index as well as the local priority we computed, using this we can define the global priority that established that based on the local priority we can define the relationship of the streams across the globally or across the all participating sites. Now when you have this information, so we know the stream priorities, and now the question is, okay, what should we build for this dissemination purposes? Now to understand what should be the first, we need to understand what should be the quality of service we need to meet. The reason is the quality of service you allocate, it impacts user expectations. And we also notice that user expectation varies with different activities. That is, if you change activities, user expectation will also change. And to understand this relationship, we use 5 different scenarios. One is video conversation, collaborative dancing, virtual lightsaber. I will already explain this. The fourth application we use is block fencing, where you can touch a block in the virtual environment, and if you can touch with your sword, you will get points, and then the next block will appear, and you have to touch it again to gain points. And the fifth application is cyber archaeology, where a person can get immersed into an archaeological site and can explore different archaeological signs in this virtual environment. Now the goal is to use those applications to understand the relationship of quality of service and quality of experience across different activities. And to measure it, we use a 3-step methodology. First, we objectively evaluate the quality of service. We subjectively evaluate the quality of experience of the users, and then we correlate the quality of experience to quality of service to quality of experience. Now to measure the quality of service, we divide the metrics into 3 different parts. One is video quality of service, cross-media quality of service, and audio quality of service. Where the video quality of service is divided into spatial domain and temporal domain. Similarly, the audio quality of service is divided into spatial and temporal domain. And for each quality of service parameters, we change the values and identify what is the quality of experience of the users. And the QoE identification were done by answering by using questions answer after the experimentation is performed. Now, what we found based on these experimentations that quality of service requirements are different for different activities. Here I give an example. We use video conversation and virtual lightsaber activities. And we found that for video conversation, users are happy as long as queue of audio and video is less than 160 milliseconds. They are not much concerned about the end-to-end delay, so they are happy as long as the end-to-end delay is less than 400 milliseconds. They require very high audio rate, and they require at least the upper body of the video streams to disseminate. On the other hand, for virtual lightsaber, they're not much concerned about the audio-visual skew. However, they require very tight interactivity end-to-end delay. They're not much concerned about the audio rate as well, but they want full upper body and lower body of the streams to interact with the other person. And also, so this means that the minimum quality requirement changes if we change the activities. Also, the priority of the priority of the resource optimizations also depends across the activities. Because if we have enough resources, which quality of service parameter we want to optimize or increase? So for video conversations, the requirement shows that we want to optimize audio rate first, and then the skew, then third is end-to-end delay, and finally is the video streams. Wherever this requirement or ordering changes if we change the activities, and in virtual lightsaber, the most important quality of service was end-to-end delay, so we want to optimize this first, and then the list here among these 4 is the audio-visual skew. So that means each activity defines its own cyber physical quality of service profiles that we need to optimize. Now there has been a lot of work that tried to perform QoS optimization in multimedia streaming. So we'll see some of them here. So to judge them or to study them, we use 4 different properties. One is multi-quality of service priority, that is they consider multiple QoS or only the bit rate or a different specific QoS. We'll see that whether the solution requires the change of QoS profiles if something changes during the session runtime. We'll also see that the runtime quality of service dynamisms are permitted in the solutions. And finally, we'll see that they consider the multi-stream 3D video, because when you have multiple 3D videos to disseminate, the challenges are different when you have a single video streams to disseminate due to the dependency of the multiple video streams. Now here are the solutions we look into. The first solution is actually for only 2D conferencing solutions, and they mainly focus on the or optimizing the bit rates. The next two solutions, which is number of video stream optimization and streaming jitter optimization, they focus on the 3D tele-immersive domain. However, they mainly try to optimize the number of video streams to disseminate rather than any other quality of service metrics. The fourth work is for video on demand applications, and in these applications, they shows that the quality of service parameters actually do depends on what type of video you're watching on your browser. If you're watching a movie, it's different than if you're watching only a song. So there is a solution that take care of dynamic quality of service profile depending on what video you are watching. However, it's not proposed for multi-stream 3D video. This is 3D tele-immersive domain, as well as they do not consider any other quality of service priorities. And finally, we have some solutions that has this multi-stream priorities and change of QoS profiles, but they're not proposed in the multimedia domain for disseminating or streaming real-time traffic. So what we need here, or we look for, is a QoS optimization problem in the session configurations. So if we formulate it mathematically, our session construction problem looks like that. We want to maximize QoS based on priority defined by activity. So we want to maximize a set of quality of service parameters, but we need to maximize based on the priority defined by the activities, provided that we maintain the minimum bound for each quality of service, which is also defined by the activities, the bandwidth bound that comes from the underlying infrastructures, and the delay bound that comes from the application. And due to this number of participants, number of streams, and the continuous values that the quality of service takes, the solution becomes NP hard. And so we represent this as a prioritized multi-objective optimization problem and propose heuristic solutions to solve this problem. Now, to solve these problems, we took the heuristic of evolutionary algorithm or genetic algorithm. Now, the reason we use genetic algorithm, I have several. The first one is genetic algorithm is one of the powerful heuristics to solve multi-objective optimization problem. Second, it works in iterations, and as Sridhar already pointed out, that we need to update the session during the session runtime, maybe frequently. So we need a solutions, even though the optimization takes longer, we need a solution that runs in iterations, so that if we find the optimization takes longer time, we can take a near optimal solutions and can use it in the current session runtime. Now, to show or to propose our algorithm in genetic algorithm, I will first give a little bit overview of how genetic algorithm works, so that everyone would know how we use this genetic algorithm in our domain. So there are several steps in genetic algorithm. The first is you have to encode the solutions. That is, you need to represent your solutions into a set of bit stream or set of representations. The first step is you need to also identify the sub-solution of your solution. So, for example, here we represent a solution with 10 bits, and each bit represents a single sub-solution. Now, step one says that you generate the initial solutions. That means you generate a solution that is valid solutions representing your problem, and then you find the n-based solution based on a rank value. Now, when you have this n-based solution, you perform a set of genetic operations on this over this solution. And genetic operation means you perform a crossover among them. The crossover means you took any two solutions from the matching pool, and you find the position where they match. For example, here they match, and then you cross over the sub-solutions to build a new two solutions. And if you see that the new two solutions are also valid solutions, you add them into the matching pool. And the step 4 includes mutations. It means that you take one of the solutions from the matching pool, you identify randomly one of the sub-solutions and replace the sub-solution with a different solution. a different sub-solution. So you get a different solution. And if the different solution is also a very solution, so you add this into the matching pool. And you run the step 2 to step 4 iteratively until you find a subsequent results give the same best solutions during the whole iteration process. Now, question is, how can you use this simple example, simple algorithm in our 3D tele-immersive session management for quality of service optimization, which also based on the priority? The first thing is we need to encode. And so encode means that we need to represent our solution which contains a set of sub-solutions. Now, if we look again, if we think again what we discussed before, our goal is to build a multi-stream dissemination graph. Now, if we divide our solutions, we can easily divide it into a dissemination graph for individual streams. So that means if we concate the solution that we develop for individual streams, we can create a solution for the whole system. So that means we can build a multi-stream dissemination graph by concatenating the solution for individual streams. Now, when we have these solutions, we can build, go for the initialization, selection, crossover, and mutations. So the first step is initialization. That means we want to satisfy QoS bounds with the minimum value, and the minimum value is defined by the activities, given bandwidth and delay bound. And unfortunately, this is also an NPR solution. So the step of optimization. So in this initial solution step, what we try to achieve is we try to build a set of initial solutions, and then we try to maximize the properties of this initial solution, or QoS optimization of this initial solution. Now, building initial solution is also an NPR. This is what I'm showing here. And to solve it, we use a viewcast, which is a priority-based preemption algorithm. And how the viewcast work here, I give an example. So we have 4 different sites, and the degree is bounded depending on the bandwidth that each site has. And we define the priority of the streams. Here, the S1A means the stream generated from site A. S2A means the stream generated from site A, the second stream generated from site A. Now, if we build a dissemination graph just constructing one by one, for example, if B wants these 2 streams, B can get these 2 streams from A. Now, if D wants it, he can also get one from A, one from B. Now, when C wants it, there is no other resources available to disseminate the stream to C. So what C would do is he preempt the lower priority stream so that he can get at least the high priority stream during the dissemination. So we get an initial solution in our genetic optimization. Now, for this 2 stream, S1A and S2A, by concatenating the dissemination of these 2 subgraphs, we can develop a full subgraph for these 2 streams. Now, if we have a different ordering of constructing the graph, for example, here we create the first B and then D, and when C wants it, instead of dropping the stream from A to D, he can drop the stream from A to B and sends it to C. So we get a different solutions. Similarly, by considering different random ordering of dropping and construction for different vertex, we can build a graph that represents the minimum solution for our genetic optimization. Now, next step is when you have the set of minimum solutions, we need to identify what is the best solution for us to use and what is the worst solutions. So that means we need a ranking functions. And here the ranking function defines a vector that contains a set of quality of service parameters where the QoS parameters x1, x2, x3 are ordered in order of their priorities. And here the requirement that we define that a rank PM or rho M is greater than rho N, that is the solution of mth solution is better than nth solution if and only if the ith parameter of mth solution, ith QoS parameter of nth solution is better than ith QoS parameter of nth solutions, provided that the previous other high priority QoS parameters are equal. Here I give an example to understand it. For example, we are considering only bit rate, delay, and skew. Now, they are ordered, the first priority is bit rate, the second priority is delay, and the third priority is skew. And if we have 2 different solutions, one is red solution, one is green solutions, though the green solution has better delay and lower skew, since bit rate is considered as the high priority for QoS parameters, we consider the red solution as the high rank than the green solution. Now the question is, if all the QoS parameters are equal, what should we consider? Now to consider, we can consider any of it, but to improve the optimization process in the to converge the optimization towards the optimal solution, we use according distance heuristics. What it does is it tries to identify for a given solution what is the variability in this solution compared to its neighbor, and neighbor is computed based on the ordering of the rank of the solutions we have. Now, if we have more variability into the QoS values, it means it will create more random offspring during the genetic optimization process, and it will ensure that we will not stuck into a local optimal solution. Now, when you have the selections done, the next step is we'll pick the random solutions from this selective set, which is called matching set, and perform a crossover among them at the point when the sub-solution matches. So we have two different solutions, and the solution here is the multi-stream dissemination graph. And in these two different solutions, G and G prime, we find that GS2B in the two solutions are equal, so we can perform a crossover at this point and can create two different solutions. And if these two different solutions are also valid solutions, we can add them into our matching pool. Similarly, we can perform a mutation where we take a random solutions from the matching pool, and we randomly select the solutions, and then we change the solutions to a different sub-solutions and get a different set of our dissemination graph. So it creates a different multi-stream dissemination graph. And if it's still a valid solutions, we add them into the matching pool. And we run this until we optimize the solutions to represent our QoS requirements. So what the OSM framework does is it first monitors the local data plane, and depending on the monitoring information, it builds the multi-stream dissemination graph. And once the dissemination graph is constructed, it sends this information in the form of session routing table to the local session controller, which conveys this information to the gateway, and then the streaming is performed. Now, to show how this works, we started with 4 sites where each site has 4 different cameras, 2 upper body and 2 lower bodies. And each site has an audio stream as well as a lightsaber stream that indicates the position of the lightsaber into the virtual environment. And we use 9 different QoS parameters, and we try to see, given a QoS priority and minimum bound, how can we optimize the quality of service allocations in the multi-stream dissemination graph. So for video conversations, we start with an initial solution which is built using Viewcast, and after 20 iterations, we get the solution which has very good audio quality and upper body, and the rate of the upper body video stream is very high. If we use the same setup and same configurations but different cyber QoS profiles, we can build the same allocation for virtual lightsaber. As you can see in the virtual lightsaber, the end-to-end delay is further optimized than the solution we constructed for video conversations, because end-to-end delay is one of the most priority stream in virtual lightsaber. And also virtual lightsaber includes the upper body and lower body video streams rate during the disseminations, where the video conversation only allocates most important rate allocation only for the higher body video stream. So that means the OSM or optimization performs what we require in this 3D tele-immersive domain. We also perform the planet level experiments to understand how it impacts in terms of number of participants, number of streams, as well as with the real-time with the network interface or internet artifacts. So with these experiments, we'll show that how the audio rates were allocated across different solutions. So the first solution is the pink color. It is the OSM if we build with the conversations, and the red one is the OSM is built for lightsaber. And since audio is most important in the conversation, it gets high allocation in the conversation activities. But if we just consider the Viewcast-based solutions, the solution is the green line, and the improvement we get by using the OSM is about more than 50%. Also, if we look into the random solutions, which is the orange line at the bottom, it shows that we get very low allocation of the audio rate if we just don't consider any prioritized quality of service profile during the session runtime. Similarly, we can show the rate allocation for lower body video streams, and how can we allocate rates or improve rates by considering this QoS optimization. We also perform the overhead. So the overhead definitely increases if you increase the number of sites. That is, if you increase the number of sites, you have a bigger graph to optimize, and you increase the number of latency if you increase the number of iterations. But the good thing is, what we found out, since if you increase the number of sites, the number of streams, the solution space or the search space you want to search for an optimal solution becomes small, because the number of resources you have is limited. And therefore, even if you increase the number of sites, the latency of finding the optimal solution actually decreases. So using this approach, optimization latency for 10 users with 4 streams per user is about 2 seconds. But however, some cases we have about 3 to 5 seconds to identify the optimal solutions in the disseminations. And that's why we use a 2-step optimization process. In the first steps, we build an instantaneous session adaptation based on a matrix. And finally, we perform the evolutionary optimization in background. When we have the optimal solution, we install this solution in the current session runtime so that the users can get better user expectation from their session. So what we present here is a OSM pipeline. And for this one, we first perform a QoS and QoE study. We build a model cyber physical QoS profiles. And based on that, we develop an optimization process and we perform objective evaluations to show that our solution meets the model that we constructed. We also perform subjective evaluations. That is, we build the solutions, we request other participants to perform the solutions using OSM. We show that about 91% people prefer OSM-based solutions than if we don't use OSM in the solutions. However, due to the time restriction, I'm not going to present these results. So what the OSM will actually provide, it improves the user quality of service during the session runtime. Now, in the OSM, we only consider the session layer architecture, that how we build the graph for only looking into the session, that we have the requirement coming from the applications, and we want to achieve this by looking only on the overlay or application layer. And we'll see that even we can improve further if we can interface the session layer to the network layer. How can we do that? Here it is an example here. So we have this multi-stream dissemination graph constructed based on the OSM. Now, if we look details that how the streams are disseminated by constructing the network layer topology as well, you can see that the gateway that is sending the streams is actually making some redundancy in the transmission. For example, the A needs to send 2 red streams from A to the local switches, whether we are looking at the local switches at the edge of the local network. If we remove this redundancy, we can get a picture on the right side that has lower overhead in terms of bandwidth we want to disseminate. And since we are using 3D images, the bandwidth savings by reducing the number of streams is very high. And since we are only presenting 2 streams here, if we consider about 5 to 6 streams from each side, the reduction of bandwidth is very high. Also, if we look into the stream dissemination, also has length, reduced length in terms of end-to-end dissemination path. And it is due to that if we can control the network layer switch to do the network replication and forwarding just by, instead of going to the application layer, we can reduce the overhead from going to the application as well as the overhead inside the application protocol. And if we use a wireless application host, it actually gives a lot of improvement in the end-to-end delay streaming. So if we can control the network layer switches, what we can achieve here, we can reduce interactive end-to-end delay in streaming, and we can reduce bandwidth consumption of redundant traffic. Now, how can we do that? We can do the control, we can perform the control of the network layer switches using a software-defined networking approach. What SDN says that before, in the traditional switching solutions, each switch performs its own decision and routing configurations. So there is no management control plane. So there is a message exchange among the switches to build the decision about the routings. On the other hand, in SDN, there is a separate controller is assigned for that, which takes care of how the routing should be done, but the switches becomes dumb, and the goal of the switch only to forward the data plane traffic. It improves the overhead as well as it improves the manageability because we have flexible control and we can control the network layer component from the application or session layer. Now, using this, how can we achieve this, achieve or improve our solutions? We develop OpenSession, which is an SDN-based multi-stream management in 3D tele-immersion. So what the OpenSession does is, first we construct the multi-stream dissemination graph using OSM that we have already described. Next, we build this session routing table and send this session routing table to the participating LSCs. And once the LSC gets it, it identifies what are the streams that need to be disseminated from the gateway, so it will not make any redundant dissemination. And also installs rules into the switches that the switch will perform replication of the traffic, and on the forwarding of the traffic, based on the required multi-stream dissemination graph. So if we can build these solutions, we can actually achieve improvement in end-to-end delay as well as in the reduction of the bandwidth. But as we see that there is no free lunch, to do this, we have several difficulties to solve. The first difficulty is multi-rate guarantee problem. For example, your multi-stream dissemination gun defines that you send different frame rate, application frame rate to different other remote participants. Now, if we want to do this using these open sessions, the problem is the network packet rate you want to maintain at the switches cannot guarantee your application frame rate. And the reason is, here I give an example, you have two application frames which is constructed based on two network packets, and for the same packet rates, which is 2 packets per second, you can get different application frame rate. And since the application frames are not constant in size, it's hard to maintain the application frame rate from the network layer switch-based dissemination. So what we want is, we want a solution, a scalable solution, so for this multi-level forwarding. It should be scalable since we should be able to accommodate any number of forwardings from these switches. Also, since the number of frame changes, it's not scalable if we update the frame size every time at the switches to identify what are the number of packets we need to disseminate. So we need to optimize. Also, we need to find the solutions to overcome this processing overload. There's another problem which is called seamless session route object problem. If we remember at the beginning of the presentation, I showed that in 3D tele-immersion we have a notion of view change. That is, we can change the views to watch a remote participant from different view orientation. Now, if we remove this control of multi-stream forwarding at the switch layer, at the network layer, we have some difficulty in the view change. And the difficulty is, for example, if we want to change the left side figure to the right side figure, where the right side figure you see that the participant C is actually changed its view. That is, he wants to receive the stream, different streams to watch the same activities from different view orientation. Now, if C drops it, the E needs to get the same stream from different other participants. Now, if we update this multi-streaming graph in different order, we'll have different problems. For example, if we add the path for DE and then remove the path for CE, we have overloading, which is create the redundant path during view change. And this is not expected, since in 3D tele-immersion we can have frequent view change, and the bandwidth of 3D images could be very large, or so there could be very high burst towards the participants. Also, if we remove CE and then add DE, we can have a disconnectivity problem. That is, at certain points, E will not get any streams, and there will be blank on the disseminations, and he will not see the streams, and suddenly after some time, he will get the streams from a different path. So we want to ensure that we will not get this overloading or disconnectivity when we perform this view change from this open session, that is from the switch-based forwarding. So first we'll see the solution that we can develop by only considering the single stream for less complexity, and then we'll show how can we achieve it for multiple stream. So if we look or replace the solution as a problem of building or changing one graph to another dissemination graph, if we look into the switch level architectures, so we have a graph G old, and we want to get a new graph G new. Remember, we're only showing the replacement for single streams, and in 3D tele-immersion, as I mentioned, there could be 10 streams for single site, and for 10 sites there could be 100 streams. So the graph is really complex when you want to build the set solution for the real setup. Now, when you have these differentiations, what we want to achieve is we want to build G old to G new without creating any disconnectivity or overloading. So the first steps we do is we create a virtual link that is at D that builds a virtual link showing the link that we need to create in the new graph. And creating virtual link will not create any problem into the dissemination path, because it tries to match the packet with new signature. And unless we change the signature of the packet, it will not be in action. So what happens is, if we have a packet with signature red, then the forwarding was happening G old as before. Even after the virtual link has been added, still the forwarding does not change. Now, if we change the signature of the packet and get a green packets, now the new signature will be meshed against the switch into the switch at site D, and then it will be disseminated to using a new path. So using this, we can actually ensure that by moving from G-old to G-new, you will not create any disconnectivity, you will not packet loss, as well as there will be no overloading in the dissemination part. And for doing these signatures, you can use source port to differentiate signatures. This is to change the value of the source port to change different versions of these packets. Now this works for a single stream. So this is a source-based atomic switch update. That is, at the source, you change the signature. So you first update the rules at the distance or remote switches, and finally, you change the signature at the source so that you can make sure that the switching is atomic. But this might not be the case when you have multiple streams. Here is an example. When you want to use multiple streams adaptations, you see that here nodes or site C drops S2B and receives S1B over the time. When you have this change, you see that concurrent route update of S1B and S2B is fine because both streams are originated from site B. So if you consider the source-based atomic switch, it would work. But if you consider the right side figure, here site C drops S2B in the new graph and receives a new stream from S1A, where the source of the streams becomes different. Now, if you cannot make the proper ordering, you will create a redundancy towards site C where S1A and S2B can present at the same time. So you need to make a proper ordering where here you need to do route update of S2B and then you want to perform route update of S1A so that this overloading cannot occur at site C. So we find out two cases that can create the dependent route updates. One case is you are dropping a stream from a different source and getting a stream from another source. Or also in case of forwarding, you are dropping the stream forwarding to a different source, different destinations, and adding a forwarding to a different destinations. So what the problem here is, we need to build a sequence of streams to perform multi-stream route updates to minimize bandwidth overloading at the participating site. So the problem of multi-stream route updates becomes now what is the order we should use when you have this huge number of streams to build and disseminate and change from old overlay to the new overlay. So we use multi-stream route update algorithm, and the algorithm works in several iterations. The first is we need to identify what are the streams that has this dependency of route updates. And for the stream that does not have any dependencies, can run the route update in parallel. And for the stream that has the dependencies, we compute a score. And a score defines that if we run this route update in the current overlay conditions, what are the number of conflicts it will create. So that means if we have the conflicts of S1A is 1, so the score of S1A becomes 1. And the conflicts that creates S2B is 0, so the conflict becomes 0 for S2B, or score becomes 0 for S2B. And then what we do is we perform the route update with the lowest score in the set. And in this case, since score of S2A and S2B both are 0, we can perform it in parallel with S1B and S2C. And since we left only S1A and S2C, by using only 2 iterations of route updates, we can perform or more change the old overlay to the new overlay. And this runs iteratively until we perform the route update for all the streams we want to perform during the view change process. So here I give a little bit details about that if we make sure that a sufficient conditions that you will not create the figure that we proposed here is the route update dependency during the overlay computations. So that means when OSM computes the graph, multi-streaming definition graph, you can put a sufficient condition or a requirement that these two conditions will not appear. So this condition, you can assure that this condition will not appear in your final dissemination graph, and then you can perform all the route updates in parallel, and it will not create any conflict. So here I give an example of how it impacts the route, the viewing performance if we cannot take care of the atomic switch. So here two persons, a video I'm showing, here two persons are performing a lightsaber activities. And if you see that if there is no open session, there is a frequent frame drops because some person is changing views. But if we use the open sessions, we don't see a frame drop because the switching is performed atomically. Similarly, there are other solutions for teletherapy exercise in 3 tele-immersions. With open session, we show that there is no drops. But if you use no open session, there is a drop of streams. So we perform evaluate our solutions with multi-party setup. where we use office network, campus network, our department network, as well as campus network. We use or put the switches at different points of the network so that we can have the control to update the switches. We use about 8 streams for each user surrounded by 360 degrees. And what we found here, or the results is interesting results are, if we use the dissemination graph represented here for different streams we're using in our solutions, what it shows here in the figure that by using OpenSessions, we can improve the local stream bandwidth, that is the bandwidth for disseminating from the local side is about 60%, over 60%. And for remote stream bandwidth, that is for by forwarding from the network layer rather than going to the application and coming back from the application, we can improve the bandwidth at about 30%, 35%. Since, as I mentioned, we reduce the length of end-to-end delay path, network delay is improved about 40%. And also, since the application is performing less receiving and less forwarding, the overhead of the application processing is also improved by about 25%. And we can show the similar graph for other participating sites as well. So the question is whether we are introducing any added complexity by updating these switches in parallel when we can do it from the session layer. So to understand this overhead, we perform the same sessions with OpenSession and no OpenSessions. We try to identify what is the view change latency happens. That is, when a user requests a view change and when the whole overlay gets changed based on the required views, new views, what is the delay we can achieve if we use OpenSession and no OpenSession. And as you can see, the overhead is increased to about 50 milliseconds if we use OpenSession, which is the maximum bound that we can introduce by using OpenSession in our solution, which is actually very reasonable. We also try to identify what is the OpenSession overhead. Since we built OpenSession using Floodlight with OpenFlow version 1.0, we use a C-bench tool to identify or benchmarking the performance of the controller, and we see that using our solutions, that we only introduce 6% overhead into the controller. That is, if we don't use our solutions, the number of packets it can process is 6% less than number of packets it can process by using OpenSession. So what we present here in OpenSession is OpenSession enables a synergy between session and network layer so that the application can drive network layer to support different application features. And I provide solution some of it. I haven't provided solution for how we achieve multiple rates, but we also develop solution for that. So what we actually achieve or try to emphasize here that since we have control in the network layers, soon the application will take this added freedom and build different application features during the streaming to configure the quality of service during runtime. And here we use these features to optimize end-to-end interactive latency, network resource optimizations, and seamless view change experience. So what in my research and my PhD, what my contribution was, I provide a session monitoring and query solution considering hierarchical structure of 3D tele-immersion and real-time requirement of application traffic. We built, this is a session monitoring and query plane. We propose distributed multi-stream dependency preservation algorithms to support large-scale non-immersive users, which I haven't covered in this talk. And we also consider user heterogeneity and activity-dependent cyber quality of service profile in multi-streaming and QoS allocations. And finally, we use software-defined networking to introduce session network synergy for QoS control in 3D tele-immersion. So at the end, so as I mentioned at the beginning, my research goal was we built the user expectation aware programmable cross-layer comprehensive session management framework for 3D tele-immersion. So sorry for my rush. If I would actually like to take any questions if you have at this point.
Hi, hello. Can you hear me now?
Yes.
Oh, yeah, good. So I have basically two questions. The first question is because we're doing the genetic optimization. Mm-hmm. So that optimization is happening online or offline?
Online.
Online. So that will introduce some delay for the application?
That's why we use a two-step optimization process.
Yes.
As you mentioned, and we are mainly interested to use genetic because it performs in iterations. Because still can get an optimized solutions. but we step two steps. The first step perform this instance optimizations, and on the background we perform this optimization of genetic algorithm to get the near optimal solution. Yeah.
Okay, so that calculate that optimization or near optimization solution is very quick, right? It's not take time so that we will sort the delay in the application. Is that correct?
Right, because we are masking with the first step. Yeah.
Okay, good. So the second question is, because we are using camera to catch the motion or picture from the users, right?
Motion of users, yeah.
Motion of users, yeah, motion of users. So we have a couple of streams for one user, for example. Then in the monitor, how do we render this 3D? Do we use some 3D construction algorithm, or are using the other technologies?
Right. So we use in our solutions we use mesh-based reconstruction for each cameras we generate. We calibrate each cameras beforehand so that the renderer can use this calibration information, and we disseminate each stream separately so that we don't need to merge beforehand to build a complete model, which can be expensive in terms of amount of bandwidth required to disseminate a single streams. And at the receiver renderer side, we just use this calibrated information and reconstruct these images, render these images on the screen.
So basically, you're taking the images from the stream, the video stream, and then construct the 3D models, right? Is that correct?
Right.
Okay. Okay, good. So you are using the available 3D construction algorithm, or you just develop your own?
Because this work is also in collaboration with University of Berkeley.
I understand.
And his group, there is a group, Gregorish Corella, Dr. Corella and Jojana Batsi's group. They are trying to focus on this part, actually building this reconstruction in real time. So we are using their algorithms in our 3D construction.
Oh, okay. Is also in your department, or is that group is from different? I just wondering, is it from different university?
From Berkeley.
Oh, from Berkeley. Okay, I see.
Yeah.
So okay. Thank you very much.
Thank you.
It's very, very good.
Thank you.
Folks, any further questions? I know there was at least one more question online that came in, and I can ask it, or the person that asked it can ask it right now.
Yeah, go ahead, Sridhar. It was from me.
Okay, yeah, you want to go ahead, Nagesh?
Yes, I just wanted to understand, what kind of compute requirements, what kind of computation requirements are there for this kind of implementation?
Right. So the computation requirement is very low in our case, and that's why we use the name as TV, which is tele-immersive environment for everybody. So we try to emphasize that we can use off-the-shelf hardware to do all the computations, and it still can achieve the real-time guarantee in the 3D applications. So in our case, we use only there's no special hardware we're currently using. It's all off-the-shelf PCs. Most of them are 4-core PCs.
But for things like the 3D reconstruction and so on and so forth, I guess to follow up on Nagesh's question, do you see, I guess, the need for things like, using GPUs and so on and so forth in the future?
Right. Actually, this effort will already started in our group. So we're trying, because before we were using the 3D Bumblebee cameras to capture this image. Now we moved into the Kinect cameras. And we're trying to optimize this performance by using GPU for that, so that we can take the reconstruction to the GPU.
I see. Actually, that brings me to the whole question of Connect, which is, I guess, does gesture recognition and motion detection, with the placement of sensors on individuals, for example, in the example of dancing that you said, does that place additional requirements, or does that simply get handled as an additional stream in your system?
Sorry, I didn't. So, what is the requirement?
So, I mean, you have cameras, you have, the sort of the things that are giving data right now that are creating streams, right? The cameras that are, now in Connect, you actually have gesture recognition, right? Where people are placing sensors on top of their bodies, and those are actually sending data inputs about location of individuals, right?
Right.
So I'm wondering whether that creates an additional sort of tele-immersive stream that you have to deal with.
This is a good question. So the only difference between what the Kinect provides and what we want to achieve here is a bit different, because in Kinect they can use this metadata information about different body parts because they use avatars to represent the person. In our case, we don't use avatar to represent the person. Rather, we use the real person's 3D model. So we are trying also to do, so that's why we need to create the 3D model anyhow from the sender side to and send it to the receiver side. The sending only the metadata is, we are actually trying to do this as well, because to optimize the bandwidth, what we're trying to do, we try to identify different part of the bodies. This is another project we're currently doing, different part of the bodies, and depending on the frequency of movement of that part, we can change the frame rate of sending streams of that specific part. So this way we can optimize the amount of bandwidth required in the transmission. But still we need to send the reconstructed image from the sender, because only sending the metadata, it's hard to recreate the very, without artifact, it's very hard to create the image, the real 3D image.
Okay, thank you.
Thank you.
Any further questions? There's one more question that has come in online, which is what needs to happen to make this real in products? That is, how far are we from actually seeing this in a product in the near future?
So the one point we're still, if you look into the quality of the bandwidth we have, the quality of the demo I presented, the quality of the image, 3D construction image, by subtracting the background in real time, it's still not perfect. That's why people are still using the avatars to do this. But if we can improve further on this area, I mean, we're currently doing this, the end-to-end disseminations with Berkeley's and within the US, and we're very successful with this product. The only bound for us, or limitation for us at this point, is the quality that we're trying to achieve here. Especially I think that the quality is the bound that we're trying to achieve at this point.
One more question. Is there any, did you guys look at any algorithms other than sort of genetic algorithms? I guess there are quite a few folks in the industry here, and so I guess when we hear genetic algorithms, are sort of, our guards go up because they tend to be pretty slow. But I guess what you've shown is it's not computationally that intensive, but there's still a fear that it might not scale.
Right. And so I agree with this point, and that's why we had to develop this two-step process. And the problem is, since if we only have the problem is only to optimize the quality of service, we try to build different greedy algorithms for these purposes. But the problem is not only optimization, we also need to maintain the priority. Also, we need to maintain the minimum bounds, and those multi-priority the minimum bound required optimization is hard to do. You can get a heuristic solution which is far from the optimal by using some greedy approach. But what we're trying to achieve, that whether a genetic algorithm would be a good use here to get further optimization in or to build the near optimal solutions, which might not be achieved using the greedy algorithms. So we try to explore different greedy algorithms as well. It's true.
Okay. So, folks, any further questions for Ahsan, Arefin? If not, then I guess a couple things. First, our next seminar will be on August 23rd, when Professor Arindam Banerjee from the University of Minnesota will be presenting a seminar on online optimization for large-scale machine learning. So please join us then. And I guess continuing in our tradition, Ahsan, what we typically do is we give the speaker a virtual round of applause. So for folks, all of you, please unmute your speakers, unmute your microphones, and let's give Dr. Arefin a warm round of applause. So thank you so much, Arefin. And the seminar slides, I've already got those. I'll be putting the recording up on YouTube shortly. Thank you very much. We'll see you all on August 23rd. Thanks.
Okay. Thank you very much for attending my talk. Thank you.